calculation. So what is lattice anharmonicity? If we do a Taylor series expansion for the potential energy of a system with respect to the atomic displacement in real space, then we have this expression. The 0th order term is the potential energy of the equilibrium position. The first order term is 0. The second order term is called the harmonic term. Any terms higher than the second order are called the anharmonic terms. At low temperatures, harmonic vibrations will describe many physical phenomena, and the anharmonic terms are often ignored. However, as temperature increases, anharmonic effects become more and more pronounced. In materials computation, anharmonic effects can be found in many physical quantities. For example, when including anharmonicity at high temperatures, the vibrational free energy differs from that calculated by harmonic phonons, which further impacts on many thermodynamic properties, such as phase transition, thermal expansivity, heat capacity, and thermal elasticity. Also, the lifetimes of scattering anharmonic phonons can be used to study the lattice thermal conductivity. In geophysics, thermodynamic properties of minerals at high temperatures are essential for geodynamic modeling. For example, thermal expansivity, isochoric and isobaric heat capacities, and isothermal and adiabatic bulk moduli. Accurate free energies, including anharmonicity, are needed for determining phase boundary, which is the interpolation of seismic discontinuities. Thermoelastic properties such as elastic coefficients Cij, bulk and shear moduli, and longitudinal bulk sound and shear velocities are needed for interpreting seismic tomography. Study of thermal conductivity of lower mantle minerals are also important in geophysics, because the way for heat to transfer influences the planetary evolution in the Earth interior. Heat transport in the Earth mantle is dominated by convection, but conduction also plays a role. The core mantle boundary, located at a depth of 2,890 kilometers beneath the Earth's surface, is the interface between the molten metallic core and the rocky lower mantle. Conduction is believed to be the main mechanism of heat transport across the core mantle boundary, where mass transport is impeded. The knowledge of kappa of the lower mantle minerals is critical for understanding the dynamics in the deep Earth. The lower mantle extends from 670 to 2,890 kilometers in depth, corresponding to 55 volume% of the Earth's whole interior. Pressure ranges from 23 to 135 gigapascal, and the temperature ranges from 2,000 to 4,000 Kelvin. Apart from the lower mantle, the subducted mid-ocean ridge basalt accumulated above the core mantle boundary. Therefore, study of the thermal conductivity of the MORB is also important for understanding the heat transport from the core to the mantle. Here are some ab initio methods to compute materials' thermodynamic properties at high temperatures. Perturbation theory plus the quasi-harmonic approximation has been successfully applied by various to various weakly anharmonic systems. The quasi-harmonic approximation neglects the intrinsic temperature dependence of phonon frequencies and treats phonon frequencies as explicitly volume dependent only. However, this method fails for strongly anharmonic systems with imaginary phonon frequencies or strong intrinsic temperature dependence of phonon frequencies. Ab initio molecular dynamics plus the thermodynamic integration is a widely used method for free energy calculations. However, to approach the thermodynamic limit, conducting Ti using ab initio MD with a sufficiently large supercell is beyond the current computational capacity. The third method is the method I'm going to introduce in this talk, the phonon quasi-particle approach plus the phonon gas model. The phonon quasi-particle approach can give us explicitly temperature-dependent phonon frequencies with a sufficiently dense Q mesh in the thermodynamic limit. The phonon gas model uses the phonon spectrum to compute vibrational entropy, free energy, and thus thermodynamic properties. Phonon is a kind of quasi-particle. It can be described by two parameters, the frequency omega and the lifetime tau, or the line width gamma. Gamma equals 1/2 tau. For harmonic approximation, omega does not depend on temperature. Phonons do not scatter with each other. Thus, the phonon lifetime is infinite. However, when we consider anharmonicity, omega becomes temperature dependent, and the phonon lifetime is finite and usually in the magnitude of picosecond. By incorporating the temperature-dependent phonon frequency into the phonon gas model, we can easily compute the vibrational entropy and the vibrational free energy, including anharmonicity. Here is the phonon quasi-particle approach. We project the atomic velocity onto the harmonic phonon eigenvectors, obtain the renormalized phonon frequency and phonon lifetime from the velocity autocorrelation function, VF for short. The velocity used in this calculation is the polarized velocity. It can be calculated from the atomic velocities obtained from ab initio molecular dynamics simulations and the phonon polarization vectors obtained from harmonic phonon calculations. So M here is the atomic mass, and capital N is the total number of atoms in the supercell in the MD simulation. Q labels the phonon wave vector, and the S indexes the three little n phonon branches of an n-atom primitive cell. For a well-defined phonon quasi-particle, the velocity autocorrelation function is an exponentially decaying cosine function, which looks like this. The single phonon power spectrum can be obtained by Fourier transform of the VAF. For a well-defined phonon quasi-particle, its power spectrum has a Lorentzian line shape with a single peak at the renormalized frequency omega tilde, and the lifetime of 1/2 tau, and the line width of 1/2 tau. The quasi-particle properties can also be obtained by directly fitting the VAF to an exponentially decaying cosine function. Then the oscillation frequency is the renormalized frequency, and the decay factor is the lifetime. After the renormalized frequencies are obtained, we next construct the effective harmonic dynamical matrix from the harmonic phonon polarization vectors and the renormalized frequencies. The effective harmonic dynamical matrix at any the effective harmonic dynamical matrix at any Q point in the Brillouin zone can be obtained by Fourier interpolation. By diagonalizing these effective harmonic dynamical matrices, the anharmonic phonon dispersions over the whole Brillouin zone, vibrational density of states, as well as phonon velocities can be obtained, all of which are temperature dependent. By incorporating the temperature dependent vibrational density of states into the phonon gas model, we can then easily calculate the vibrational entropy, including anharmonic effects. In principle, anharmonicity to infinite orders in perturbation theory are captured in our phonon quasi-particle approach. From the relaxation time approximation of the linearized Boltzmann transport equation, we know that the lattice thermal conductivity equals the summation of a phonon's specific heat times mean free path times velocity times mean free path for all phonon modes over the Brillouin zone. The phonon mean free path equals the velocity times the lifetime. And at high temperature, the heat capacity is approximately kb, the Boltzmann constant. Therefore, from the quasi-particles, we can obtain the phonon velocities and the phonon lifetimes. Then we can calculate the lattice thermal conductivity. Next, I will talk about the application of the method to a simple crystal silicon with diamond structure. Here I choose silicon because it has a simple structure with a 2-atom primitive cell. The anharmonicity of silicon is generally considered to be not strong. In addition, neutron scattering data for silicon is available, so we can compare the temperature-dependent phonon dispersions with experimental measurements. Here are the ab initio MD simulation details. PBE was chosen for the exchange correlation functional. 4x4x4 supercells equivalent to 128 atoms were simulated in the NVT ensemble. Each MD ran for 50 picosecond with a time step of 1 femtosecond. Temperatures were controlled by noisy dynamics. Here I show the anharmonic phonon dispersions and the density of states at 600 and 1200 Kelvin, compared with those obtained by perturbation theory. The vibrational density of states were obtained with a 20 by 20 by 20 Q mesh. We can see that as temperature increases, there is clearly a red shift in the phonon frequencies. Next, I will compare the frequency shifts obtained from phonon quasi-particles to the neutron scattering experiments. Since the MD were simulated in the NVT ensemble, we obtained renormalized frequencies first at constant volume. Here are the obtained renormalized frequencies at 3 Q points in the Brillouin zone for 5 phonon modes. By using the following formulas, frequencies at constant volume can be converted to constant zero pressure condition. Gamma QS here is the mode Brunelson parameter, and alpha bar here is the average thermal expansivity. Then we can obtain the frequency shifts at constant zero pressure. The TO-LO mode at gamma point, the TA and TO modes at X point, and the TA and TO modes at L point all agree well with experiments. As you can see, the temperature-dependent phonon frequencies obtained from phonon quasi-particles agree well with neutron scattering experiments for different Q points in the Brillouin zone. This validates the present phonon quasi-particle approach. Next, I will talk about the application of the method to some more complex systems. First is the magnesium silicate perovskite, which is well known to be weakly anharmonic. It is the most abundant phase in the Earth's lower mantle, about 75 volume%. It has PBNM space group with a 20-atom primitive cell. Here are the ab initio MD simulation details. LDA was chosen for the exchange correlation function. 2x2x2 supercells equivalent to 160 atoms were simulated in the NVT ensemble. Each MD ran for 60 picosecond with a time step of 1 femtosecond. Temperatures were controlled by noisy dynamics. From available experimental results, we know that Raman active modes of magnesium perovskite have some irregular thermal shifts under 700 Kelvin. As temperature increases, some modes frequency remains unchanged. Some modes frequency increases, and some modes frequencies decrease. We will see whether the phonon quasiparticles can reproduce such irregular frequency shifts. So first, renormalized frequencies were obtained at constant volume. Then we use the formulas introduced above to convert omega at constant V to constant P at 0 gigapascal. So for the experimental Raman modes, we successfully reproduced the irregular phonon frequency shifts. Some frequency remains constant, some increases, and some decrease. Then by Fourier interpolation, anharmonic phonon dispersion was obtained and compared with that obtained by perturbation theory. Here I show the anharmonic phonon dispersion at 1500 Kelvin. It can be seen that in the Brillouin zone, the irregular frequency shifts generally exist, including red shifts, blue shifts, and unchanged phonon frequencies. Then vibrational entropy and the free energy were calculated with 2x2x2 Q mesh directly sampled by the phonon quasiparticles. Thermodynamic integration from ab initio MD with 2x2x2 supercells were also conducted for comparison. Results by these two methods compare well with each other, meaning that the present phonon quasiparticle approach well captures the anharmonic contributions to the vibrational entropy and free energy. From the Fourier interpolation, we further evaluated the entropy and free energy with a dense converged 10x10x8 Q mesh. And there is a noticeable deviation from results obtained with 2x2x2 Q mesh. Such difference can impact significantly on the phase boundary and thermodynamic calculations. However, conducting TI from ab initio MD with a large 10x10x8 supercell is beyond the computational capacity. The present method can overcome such difficulty in accurate free energy calculations. So renormalized frequencies can be used for accurate free energy calculations, while the phonon lifetimes can be used to calculate mean free path and lattice thermal conductivity. In terms of phonon mean free path and lattice thermal conductivity, the minimal mean free path is a phenomenological explanation of the saturation behavior of kappa at high temperatures, but lacks rigorous proof. It claims that a phonon should propagate at least an interatomic distance or a smallest crystal lattice parameter. Therefore, at high temperatures, this saturation of mean free path leads to a higher kappa than the theoretical expected 1/T relation. However, after careful thought, we realize such minimal mean free path theory does not hold true. The optical phonon branches at the Brillouin zone center usually have 0 group velocities. Phonon quasiparticles with 0 or close to 0 velocities can certainly have mean free path lower than the lattice parameter. This makes the minimal mean free path theory a myth. Apart from the velocity perspective, we also did not observe the saturation behavior of phonon lifetimes at high temperatures. Here, for magnesium perovskite, we collected the temperature-dependent phonon lifetimes from phonon quasiparticles. We can see that as temperature increases, the VAF decays faster. The corresponding power spectrum exhibits wider line width, indicating that the phonon lifetime depends inversely on temperature. Phonon lifetime decreases as temperature increases. Therefore, at sufficiently high temperatures, the phonon mean free path can be lower than the lattice parameters. and no saturation behavior of the mean free path or the kappa was observed. Also, the mean free path roughly obeys the 1/T law. We further applied the phonon quasi-particle method to magnesium silicate post-perovskite. Magnesium silicate perovskite is believed to undergoes a structural phase transition to post-perovskite above 125 gigapascal and 2,500 Kelvin. Therefore, magnesium post-perovskite is the most abundant phase in the lowermost mantle, also known as the D double prime region. It has CM-CM space group with a 20-atom unit cell. The structure of magnesium post-perovskite is an anisotropic layered structure, so it can be further simplified to a monoclinic 10-atom primitive cell with 10 atoms. Here are the ab initio MD simulation details. LDA was adopted. 3x3x2 supercells equivalent to 180 atoms were simulated in the NVT ensemble. Each MD ran for 50 picoseconds with a time step of 1 femtosecond. Temperatures were controlled by noisy dynamics. To obtain phonon quasi-particle properties, the velocity autocorrelation functions were fed to the exponentially decaying cosine function. The fitting was conducted till the oscillation amplitude decays to its half maximum. Conducting the fitting for several more oscillation periods leads to negligible changes in omega tilde and tau, meaning the convergence of the phonon quasi-particle properties. On the right, I show the collected phonon quasi-particles line width versus renormalized frequencies at different temperatures. Next, I compared the temperature dependence of phonon dispersions of both magnesium post-perovskite and magnesium perovskite at the same PT conditions. It can be seen that the frequency shift of magnesium post-perovskite is also small, meaning that post-perovskite is also weakly anharmonic, and its anharmonicity is comparable to that of magnesium perovskite. Phonon quasi-particles were obtained with 2x2x2 Q-mesh sampled by the MD simulations. To obtain converged thermal conductivity, we also want to obtain phonon lifetimes and the phonon velocities with a dense Q-mesh. To do that, phonon lifetimes were evaluated with a dense Q-mesh relying on the frequency dependence of phonon line width, and the velocities were computed by taking derivative of the anharmonic phonon dispersions. Then thermal conductivity was calculated with a dense 10x10x10 Q-mesh. Kappa were obtained at different volumes and temperatures. To obtain the VT dependence of kappa, geoscientists often fit kappa to the relation shown on the right. So T reference and V reference are chosen reference temperature and the reference volume. The choice of VREF and TREF and VREF is not unique, but does not change the VT dependence of kappa. So kappa ref A, B, and C are fitting parameters. Then by fitting to this relation, we obtain the function of kappa. We obtain kappa as a function of VT, shown as solid curves. For more practical use of geoscientists, kappa as a function of pressure and temperature is desired. Therefore, kappa of VT was converted to kappa of PT by utilizing the quasi-harmonic equation of state. The obtained results are shown on the right. A noticeable feature for kappa is that at constant temperature, it depends linearly on pressure, which is a typical feature for lower mantle minerals observed by both experiments and computations. The calculated kappa at room temperature compare well with available experimental results, also at room temperature. With kappa of PT obtained, Kappa of magnesium post-perovskite was modeled along the typical geotherm with a thermal boundary layer above the core mantle boundary. It was compared to that of magnesium perovskite. We found that in the D double prime region below 2,600 kilometers, a magnesium post-perovskite kappa is around 25% larger than that of magnesium perovskite. So this is mainly caused by a post-perovskite smaller primitive cell. Magnesium post-perovskite has a primitive cell with 10 atoms, while the perovskite has a larger one with 20 atoms. Due to perovskite's larger primitive cell, its phonon dispersions are folded into a smaller Brillouin zone and show less dispersive phonon branches with lower group velocities. Thus, the post-perovskite has generally larger velocities. More importantly, the major contribution to the thermal conductivity are the three acoustic branches with large phonon velocities and long phonon lifetimes among all phonon branches. The proportion of acoustic branches for post-perovskite is 3 out of 30, but for perovskite, this proportion is 3 out of 60. So when summing and averaging over all phonon modes, magnesium post-perovskite's higher proportion of acoustic branches also leads to its higher kappa. Therefore, there is a kappa increase due to structural phase transition from magnesium perovskite to magnesium post-perovskite. Next, I will talk about the application of the method to a strongly anharmonic system, calcium silicate perovskite. Calcium silicate perovskite is the third most abundant mineral in the Earth's lower mantle, which constitutes about 7% of the pyrite mantle. Calcium perovskite is more abundant in the subducted mid-ocean ridge basalt. It constitutes more than 23% of the MORB. Study of calcium perovskite's thermodynamic and thermoelastic properties as well as thermal conductivity is critical for geophysical modeling of both the lower mantle and the MORB. Despite its importance, reports of calcium perovskite thermal properties are scarce due to the challenge in dealing with its strong anharmonicity at high temperature and high pressure conditions for both experiments and computations. It is known that calcium perovskite adopts the cubic phase at lower mantle conditions. It adopts various tetragonal and orthorhombic phases at low temperatures, and it only adopts the cubic phase at high temperatures. For example, temperatures higher than 600 Kelvin at lower mantle pressures. Experimental measurements of cubic calcium perovskite are challenging at high PT conditions. Thermoelasticity of calcium perovskite was measured recently by the following two works. The bulk and shear moduli can be derived from the measured longitudinal and shear sound velocities. However, the experiments were conducted below the lower mantle pressure temperature range, and the results were extrapolated to the entire lower mantle. Also, the measured shear moduli are substantially lower than the predictions by computations. Calculations of cubic calcium perovskite's thermal properties are also difficult due to the existence of imaginary phonon frequencies from perturbation theory. The imaginary harmonic phonon frequencies are associated with a ground state double well potential with respect to the finite displacement along the R25 angle vector. For such strongly anharmonic system with ground state double well potential and imaginary phonon frequencies, the conventional perturbation treatments relying on finite displacement methods to calculate anharmonic phonon properties without renormalization of force constants fail. Therefore, we carried out ab initio MD simulations for cubic calcium perovskite and applied the phonon quasi-particle approach. LDA was chosen for exchange correlation functional, and MD was conducted in the NVT ensemble. Each MD ran for over 60 picoseconds with a time step of 1 femtosecond. Temperature was controlled through the noisy dynamics. The coupling between the dynamical stabilization of the cubic phase and the validity of the phonon quasi-particle picture was confirmed. Here in real space, the distributions of atomic displacements of oxygen atom with respect to the cubic phase equilibrium position from MD simulations are shown. At temperatures below 600 Kelvin, for example, 300 Kelvin and 150 Kelvin, the oxygen atom tends to deviate away from the cubic phase equilibrium position. This indicates the dynamical instability and distortion of the cubic phase. And an effective double well potential still exists at 300 Kelvin. However, at 600 Kelvin and temperatures above, the cubic phase is dynamically stabilized. Then we use the phonon quasi-particle approach to check the validity of the phonon picture. Here we show the single phonon power spectrum of the soft acoustic R25 mode. It has imaginary phonon frequencies from harmonic phonon calculations. At low temperatures, for example, 300 and 150 Kelvin mentioned above, the power spectrum exhibits non-Lorentzian line shape with double peaks, indicating the breakdown of the phonon picture. However, at 600 Kelvin and the temperatures above, the phonon quasi-particle is well-defined with single peak Lorentzian line shape, which is in line with the dynamical stability of the cubic phase in real space. So this non-cubic to cubic structure phase transition is a second-order phase transition, which happens below 600 Kelvin at this shown pressure. The transition temperatures agree well with several previous experiments. We further check the validity of the phonon quasi-particle up to 4,000 Kelvin. It is found that with increasing temperature, once the cubic phase is stabilized, the phonon quasi-particle remains well-defined before melting. Both the long-lived phonon quasi-particles and the short-lived ones are well-defined at high temperatures. Here I showcased some results at 2000 Kelvin. For such well-defined single phonon spectrum, distinguishable from other phonon modes, the linearized Boltzmann transport equation can be used to calculate the lattice thermal conductivity. The phonon mean-free path can be obtained by multiplying the velocity and the lifetime. We once again observe the submineral mean-free path at high temperatures, smaller than the cubic lattice parameter A. Here are the collected data for all phonon modes at different temperatures. I choose 3 phonon modes and show their mean-free path as a function of temperature. In the temperature range shown here, one mean-free path remains longer than A, one remains shorter than A, and the other crosses the lattice parameter. No saturation behavior was observed, and the phonon mean-free path roughly obeys the 1/T law. To calculate free energy and thermodynamic properties of calcium perovskite, the quasi-harmonic approximation formula is no longer valid for 2 reasons. First, the phonon quasi-particle frequencies are intrinsically temperature dependent, while quasi-harmonic approximation treats phonon frequencies as intrinsically temperature independent. Second, the phonon quasi-particles of the cubic phase are not well defined at low temperatures, so we cannot use quasi-harmonic approximation formula. However, within the phonon gas model, the vibrational entropy formula is still valid. The temperature-dependent phonon spectra can be used to compute vibrational entropy. Then Helmholtz free energy. The Helmholtz free energy can be calculated by the integration of the vibrational entropy. Since the phonon quasi-particles are only well-defined at high temperature, a reference temperature at T0 equals 1500 Kelvin was chosen as the integral lower bound. The reference DFT energy is the time averaged internal energy obtained from the MD simulations at T0. Then we integrate the entropy to obtain the free energies at temperatures above T0. From the free energy, all the thermodynamic properties can be obtained. Here are the obtained temperature-dependent phonon dispersions. The R25 mode with imaginary harmonic frequencies now has well-defined phonon quasiparticle with real frequency. The vibrational density of states were obtained with a dense converged 20 by 20 by 20 Q mesh. Then vibrational entropy was computed using these temperature-dependent vibrational density of states. Here I show the entropy as a function of temperature at different volume. The calculated equation of state was compared to experimental results obtained at lower mantle conditions around 600 Kelvin. The discrepancy between computations and experiments should be caused by the total energy error originating in the DFT calculations. For practical applications for geoscientists, the energy correction was made to the reference DFT energy with reference to the experimental data to bring the calculated equation of state into full agreement with the experimentally measured ones. The generalized Conk-Sasson scheme was used. The corrected equation of state agrees very well with the experiments. Once the correction is done at experimental temperature, the same energy correction was applied to other temperatures in our calculations. Next, the free energy was obtained by entropy integration. Results obtained before and after the EOS correction are shown as dashed and solid curves, respectively. Note the DFT energy correction is temperature independent and does not include anharmonic effects. Anharmonicity, in principle, is adequately addressed by the temperature-dependent phonon quasiparticles and included in the vibrational part of the free energy. To attract interest from both physicists and geoscientists, results labeled as before and after correction using the same vibrational entropy, including full anharmonicity, are shown as dashed and solid curves here. Also in the following slides. Here are the obtained thermal expansivity and isothermal bulk modulus. Our obtained thermal expansivity is nearly temperature independent, which is an indicator of the importance of anharmonicity. The relatively stronger temperature dependence and overestimation of thermal expansivity, especially at low temperatures, at high temperatures, as reported by previous studies, which are shown as dashed dot curve, is an indication of insufficient capture of anharmonicity. Here are the obtained thermodynamic Gruneisen parameters. Our obtained Gruneisen parameter is nearly temperature independent and shows slightly negative temperature dependence. Results before and after correction do not show too much difference. Therefore, the Gruneisen parameter is an important indicator of anharmonic effects only. Results by previous studies shown as dashed dotted curve here show discernible positive temperature dependence, which is also a lack of an indication of lack of capture of anharmonicity. Here are the obtained isochoric and isobaric heat capacities. For the isochoric heat capacity, 3 nkb is both the Dulong-Petit classical limit and the high temperature limit within the Debye model for harmonic crystal with temperature independent phonon frequencies. Here, by using the frequencies solely obtained at 1500 Kelvin, CV converges to such limit. However, by using the temperature-dependent phonon spectra, the obtained CV can be higher than such limit at high temperatures. This is another indicator of anharmonic effects. The obtained isobaric heat capacity can be used to obtain thermal conductivity for experimentalists. Here are the obtained adiabatic bulk modulus as a function of temperature and pressures. Comparisons with previous studies were also made. The last application I will talk about is strongly anharmonic metal, beryllium. Beryllium has many practical applications. It can be used as radiation window. It can be used as lightweight structural components in high-speed aircraft, spacecraft, and satellites. It has some nuclear applications. Also, it can be used as a neutron sources in laboratory devices. Beryllium has two structures, BCC and HCP. I will show the use of the phonon quasi-particle approach to determine its phase boundary between the BCC and HCP structures. Here are the ab initio MD simulation details. PBE was chosen for the exchange correlation functional. For metallic beryllium, the finite temperature Mermin functional was used. 4x4x4 supercells equivalent to 128 atoms were simulated in the NVT ensemble. Each MD ran for 50 picoseconds with a time step of 1 femtosecond. Temperatures were controlled by Nosy dynamics. Here I show the obtained anharmonic phonon dispersions at 1000 Kelvin compared with those obtained by perturbation theory for both BCC and HCP structures. The BCC structure is unstable at low temperatures. However, at low temperatures, therefore, the phonon dispersions obtained by perturbation theory show imaginary phonon frequencies. However, at 1000 Kelvin and the temperatures above, phonon quasi-particles become well-defined, and the phonon dispersion gets rid of the imaginary frequencies. The HCP structure is stable at both low temperatures and high temperatures. The anharmonic phonon spectrum of both phases were used to compute the vibrational entropy and the free energy. As mentioned above, for calcium perovskite, we used the entropy integration to compute the free energy. Reference temperature T0 was chosen to be 1000 Kelvin. And the reference DFT energy is the time averaged internal energy obtained from MD at T0. Apart from vibrational entropy, the electronic contribution to the entropy should also be integrated for metallic beryllium. So both E and S electron can be obtained from ab initio calculation software, while the S vibrational was computed from the quasi-particle spectrum. Vibrational entropy was computed with a dense converged 20 by 20 by 20 Q mesh, and Helmholtz free energy was obtained. F as a function of Vt for both phases are shown here on the left. To obtain the phase boundary, Gibbs free energy is desired. Therefore, Gibbs free energy was obtained by adding the PV term to F, and the free energies as a function of Vt were converted to functions of Pt by using the equation of states. By comparing the Gibbs free energies for both phases, the pre-melting phase boundary between BCC and HCP structure were obtained at the low pressure range. The shaded area here indicates the computational uncertainties. Accurate free energy calculations by the present phonon quasi-particle approach enable the discovery of a narrow region where BCC structure is stable before melting. So finally, I will talk about some practical details about how to perform the phonon quasi-particle calculations. The code to perform the such calculations, PHQ, can be downloaded from this link. Just a quick review of the method. In order to compute the mode projected velocity autocorrelation function, results from two ab initio calculations are required. One is the molecular dynamics simulations, and the other is harmonic phonon calculations. After ab initio calculations are done, there are 4 input files to prepare for the PHQ code. So scf.out provides the information about the primitive cell structure. din.out provides information about the harmonic phonons. md.out provides the atomic trajectories obtained from MD simulations. And input, it provides settings for the PHQ code. I will talk in details about how to prepare these 4 input files. So first, let's look at scf.out. N-tab is the number of elements, and N-atom is the number of atoms in the primitive cell. For silicon, we have only 1 element and 2 atoms per primitive cell. For the mass tag, for each element, we write down the element name followed by its atomic mass. So lattice parameter is a constant in unit of Bohr radius. For the cell parameters, it provides the 3 lattice vectors scaled by the lattice parameter. And finally, for atomic positions, we write down the atomic positions for each atom in crystal coordinates, following the element's name. Next is a din.out. It's simply a concatenation of all the din.mat files by the ph.x executable in the quantum espresso package. After we do the harmonic phonon calculations by using ph.x, the information of dynamical matrix at each Q point in the Brillouin zone is written to a din.mat file. Therefore, to obtain the din.out file, we can simply cat all the din.mat file together to get din.out. Next, let's look at the md.out. So first, the total step is the total number of ab initio MD steps. It's used to claim memory in the code. So you can write down a large number for this. After the atomic positions tag, we put the equilibrium atomic positions of the supercell in the supercell's crystal coordinates. So as you can see, this is the equilibrium positions for 128 atom supercell of silicon. For each MD step, we first put the step number. Then after the atomic MD positions tag, we put the atomic positions in the supercell's crystal coordinates. Finally is the input file. So first, dt is the time step for MD simulation in Rydberg atomic unit. Step MD used is the MD steps we want to use for the calculations in the code. Correlation time indicates the correlation time to calculate for the velocity autocorrelation functions in unit of dt. Pole is the parameter used in the maximum entropy method to filter high frequency components. Later, I will talk about the maximum entropy method. Supercell indicates the supercell size we used in the MD. Temperature is simply the MD's temperature. And finally, by setting the method tag, we can select quasi-particle properties obtained by which method to construct the effective harmonic dynamical matrices. For example, when method equals 0, it means the curve fitting method is used. The VAF is fit to an exponentially decaying cosine function. Method equals 1 means the Fourier transform is used, and the Lorentzian shaped power spectrum is used to obtain phonon quasi-particle properties. And the maximum entropy is another method to obtain the quasi-particle properties, which should also yield the Lorentzian spectrum. So PHQ is a serial Fortran code. After compiling the code, simply type this command to run the program. Here I show some of the output files. The obtained renormalized frequencies will be written to the file frequency.freq. The first column are the indices of the phonon of all the phonon modes. The second column are the harmonic frequencies. The third, fourth, and fifth columns are the renormalized frequencies obtained by the three methods: curve fitting, Fourier transform, and the maximum entropy method. As you can see here, for well-defined phonon quasi-particle and converged calculations, the three methods yield very close renormalized frequencies. The obtained effective harmonic dynamical matrices will be written to the dynamical Oh, sorry, wait a minute. I think someone is knocking at the door. Oh, sorry, I'm having a meeting. Yeah, you can. Okay. The obtained effective harmonic dynamical matrices will be written to the DNMAT MD file. The format of these files resemble the format of the DNMAT files output by the ph.x of the quantum espresso. So users can use these DNMAT MD file to further compute anharmonic phonon dispersion and the vibrational density of states. To compute anharmonic phonon dispersion and vibrational density of states, the Fourier interpolation can be done in two steps by using the tools provided by the quantum espresso package. First, the Q2R.x executable performs the Fourier transform from reciprocal space to real space. Second, the matdin.x executable performs inverse Fourier transform from real space to reciprocal space. Examples of input file for Q2R.x and matdin.x are shown here. Yes, that's it. Thank you.
Okay, thank you very much, Jean. Thank you very much. Do you have any questions? We'll take questions now.
Okay, yeah.
Jean, I have a simple question.
Okay.
So at high temperatures, we know that everything should obey the Dulong and Petit rule, right? So that the heat capacity is no, that's for heat capacity.
Yeah, that's
at high temperatures. Don't we know the behavior? Yeah, that's for heat capacity.
Yeah.
For at high temperatures. Yeah. So do you need the anharmonic properties at high temperatures, or you can just use the Dulong and Petit approximation?
So you mean whether we can use quasi-harmonic approximation for these for the
no, what I mean was like okay, for instance, how come your blue line, your black line is is not going to a
I see what you mean. Yeah. So because calcium silicate perovskite is strongly anharmonic, it does not have a well-defined phonon quasi-particles at temperatures below. So here I just use a renormalized phonon frequency at 1500 Kelvin to compute CV. So since this phonon frequency is temperature independent, we can only get this converged CV to 3 nkb. Yeah, this is the behavior of the harmonic phonon. Though we use the anharmonic phonon frequencies, but since we only use this the omega at one temperature, it converges to this limit. However, if we use temperature dependent omega, then it can be higher than this limit. Yeah.
Okay. Yes. I see. I understand. Yeah. Thanks.
Yeah.
Other questions? Okay. Okay. So thank you very much again, Shen, for the.
Sorry, I have a question.
Okay.
Oh, sure.
Yeah, thank you for your nice presentation. My name is Innocent. I'm from the University of Rwanda.
Okay.
So I'm curious to know if these calculations are dependent to the size of the material. Actually, I'm thinking this if it could be applied to nanoparticles or nano-sized materials.
Okay. So yeah, of course, the method can be applied for various kinds of materials. The main limit is the computational capability. So if you want to simulate like thousands of atoms, then maybe ab initio MD will encounter some difficulty. So here I usually simulate these systems around several hundreds of atoms. Yeah, of course, this method can be applied to several other nano systems, but yeah, the main problem is the ab initio MD capability.
Okay.
Okay, thank you.
Okay. So I think thanks again, Jen. If you have more questions for Jen, for instance, you want to know how to run the code, which I want to learn. We are going to have a breakout room, and we are going to have breakout sessions. We have, apart from Jen, who will be there to discuss about running the code, we have 4 other posters, people giving posters. One will be given by Fallon, another by Rene, a third one possibly by Christian. I don't know if Christian is around. I think he's around. And then a fourth one by Jonah Nagura. So what will happen is, at this moment, I'm going to open all the rooms, and then you'll be able to choose which room to go to. I don't have the title of the posters on it, but you go to each of the room. You can go to one room, and then after a few minutes, go to another room. After a few minutes, go to another room to discuss with you person. And then the presenters, you go to the room that has your name, and then when you are in the room, you share your screen, and then you can discuss with people. Now we are trying to make sure that there's somebody in the rooms to help you, but for the presenters, just go to the room, share your screen, and then you'll be able to present. Okay. Does anybody have a question before we start? Okay. If you can't go to a room, if for some reason you have an old version of Zoom, I can't go to a room, I'll stay a little bit in this general place so that I can put you in a room. So I'll open all the rooms now, and then you choose a room to go to. Okay, thank you. Jen will be in room 1, okay, to discuss, yeah. And then
Yes, I'm Mr. Rene Costa.
Yeah, Renee, you need to join your room. Do you
Oh,
see? Yeah.
Yes, I'm here.
Okay, one of the rooms is yours.
Okay.
So let me assign you to your room. You should be able to join.
Okay.
Okay, but let me assign you because everybody
Okay.
needs
Okay.
you to.
Okay.
Okay, so can you? Okay. Okay. If you need help joining a room, maybe for some reason you cannot join, because if you have an old what do you call it, Zoom client, you may not be able to. If you need help, just let me know and I will put you in the appropriate room or put you in a room. So Gabriel, Philip, okay, Gabriel moved. Philip, Willie, Prof. Kofane. So I can put you in a room if you tell me which room you like to go to. You have approximately like 10 minutes to be in the room. But you can also move from room to room within the 10 minutes. Okay, Philip, which room do you want to be in?
I don't know what is in the rooms. I have not checked.
Oh, okay. Let me put you in the room by Renee. So I'll move you to Renee's room. Unfortunately, I didn't put the titles. So, yeah.
Okay.
So I assigned you. Yeah. What about you, Willie? Which room do you want to go to? You can discuss with Jean in room 1 or go to the poster by Fallon or poster by Renee or poster by Kristen or poster by Jonah. Willie, which room do you want to join? Presley, Salah, which room do you want to join? If you tell me, I can assign you to the room.
So Omu,
Yeah.
it's Amy. Just so you know, I'm recording Fallon's presentation. I said I could record, so I asked her. She said that was okay. So now I'm going to go check on Renee's talk in his breakout room. And I checked on Jonah, and he didn't need any assistance. So I'm going to check on Renee.
But maybe Jonah wants you to record too.
Could you say that again?
I said maybe Jonah wants you to record also.
Jonah said he didn't want it. He wants to keep it more private. So I said, okay.
Okay, no problem.
Yeah, I asked them and they said no. So I said, okay.
Okay, it's fine.
Okay, I'll be back in a minute.
Thanks. Yeah, sure. Elika Wabululu, which room would you like me to assign you to? Let me assign you to the room with Jen. Elika. Willie, let me assign you also to the room with Kristen. Presley, I can assign you also to the room by Kristen or Renee. OKE, I will assign you to the room by Christian. Maybe Prof. Kofani. Let me assign you to the room by Jen. So you discuss with him. And then I will also want to join the room. Let me join the room by Jen.